Welcome back. I'm Daniel, and in this lesson we will discuss recursive types and auto-bounded types, a situation known as F-bounded polymorphism. Although this lecture will be purely practical, it will be a little bit more conceptual, so I'd like your full attention here so that you don't miss any line of argument. Alright, so in the IDE, in our type system package, let's create a new Scala application and let's name this F-bounded polymorphism. We'll see what F-bounded polymorphism is in a second. For now, make this application extend app. And let's discuss a little design problem. The problem goes like this. I often see this. It says basically, hey, I have a class hierarchy. How do I force a method in the super type to accept a current type, quote unquote current type? So let me give you an example. Let's say I have a trait animal, which has a method, let's say breed. And this guy returns a list of animal. Okay, so this animal breeds and returns a list of animals. And the problem here is that if we say a class called cat extends animal, and we'd like to override the breed method, we would like this to, instead of returning a list of animal, we'd like this to be a list of cats. Not of animal, but of cats. And again, if I do a class dog, for example, we'd like this to be a list of dog. So the question is, how do I make the compiler force this somehow on me? So let's comment this out. Let's copy and just comment this out. I'm going to try multiple options on this problem. So I think you understand the problem by now. We want each override to return a specific list. So of course I can say that this is a list of cat and this is a list of dog. All right, but that's due to my due diligence because I am a responsible programmer and I take care that my return types are as specific as possible. And this is also legal because list is covariant, so I can put in a more specific list as the return type and this is a valid override. But the compiler doesn't prevent me from making mistakes because I'm also human. So I can say that this is a list of cats, for example, and this would also be valid code, but this is also wrong. So this is the question. How do we make the compiler force type correctness on us so that we don't make mistakes when we write the code? Now, because this solution is so error prone due to our potential mistakes, let's call this solution Solution 1, naive. And let's comment this out and let's consider another option. So let's paste this again and let's think of it another way. A solution that we sometimes see in practice is to add a type parameter here for animal. Let's call this A. And this type parameter here is upper bounded or must extend. And watch this. I'm going to say animal A. So notice how animal here appears in its own type signature. This is called a recursive type. And this particular recursive type with this kind of bound is called F-bounded polymorphism. So we can now say that the breed method returns a list of animal A, and the cat extends animal cat. So by the virtue of cat extending animal cat, then breed must return a list of animal cat. Otherwise, this would not compile. If I say animal dog here, this will not compile. So it must be an animal cat. This is how the F-bounded polymorphism forces the return type to be an animal of our specific type. So we can say dog extends animal dog, and the breed method returns a list of animal dog. So this is our solution number 2 with F-bounded polymorphism. Notice how the return types are aligned now. Cat breeds to cats and dog breeds to dogs. This is used in practice, for example, in ORM frameworks and APIs. For example, when you see a trait called entity, which denotes something that may be stored in a database, and it's actually type annotated with a type E, which is upper bounded in entity E. This is an F-bounded polymorphism example, and this is often present in database APIs, so in ORMs. Often we use F-bounded polymorphism for comparison as well. So when you see a class, say person, which extends comparable from Java Lang, comparable person. If you're a Java guy or girl, you might have seen this in practice. A class of a given type extends comparable of that same type, and it overrides a method called compareTo, which takes that same type as argument. So this is another example of f-bounded polymorphism. But this solution also has its limitations because, again, I am a programmer, so I'm human, so I can make mistakes. So I can say a class crocodile, for example, extends animal dog with an override def breed method completely correctly implemented as a list of animal dog. So this is compilable code. So if I right click and recompile, this is fine, but this is also wrong because crocodile needs to extend animal crocodile. So the problem now becomes, how do I enforce, or how do I make the compiler enforce that the class that I'm defining and the type A that I'm annotating it with are the same? So this is a complicated problem, and this introduces the solution number 3. And if you'd like, you can pause the video and think of a technique that we used in this chapter that might help with constraining a type. Alright, so you can pause the video for a few seconds and think about it, because we recently discussed a technique for type constraints. So if you thought about this, you would probably have figured that we can use this f-bounded polymorphism technique in conjunction with self-types. So let me copy this over and let's comment the entire solution number 2. And let's copy this over to solution number 3, and let's use a self-type by saying self typed A. So basically the constraint is that whatever descendants of animal A I may implement, they must also be an A. So in this example with cat extends animal cat, then cat must also be an animal cat. And I cannot say, for example, class crocodile as before. So if I try to do this, class crocodile extends animal dog, then the compiler will complain saying illegal inheritance, self-type crocodile does not conform to A, which is dog. So the basic compiler mechanism is, okay, the generic type here, the type annotated is dog, so A here is dog, so the trait animal A must also be an A, so the type that I'm currently defining must also be an A, which is dog in this case. So crocodile must be dog, which is impossible. Okay, so the compiler yells at us and our constraint is met. So this is pretty cool. We basically solved our entire problem. We forced our breed method to return a list of a specific type, and we forced other types to extend animal of that same type. So crocodile cannot extend animal of another type but crocodile. But if we thought we won, we would be wrong, because this also has some limitations. If, for example, I bring this two-class hierarchy down one level, so if I create a small trait, let's say fish, which extends animal fish, okay, this conforms to the self-type constraint. But if I do, for example, class shark extends fish, and I override breed, notice what the type signature here is for breed. So breed returns a list of animal fish, not of animal shark. I can just as well copy this class over and say class cod extends fish, and this has some breed implementation, and the shark breed implementation would be a list with a new cod. This is perfectly compilable code because a cod is an animal fish, but this is wrong, because sharks now suddenly breed to cods. And here, my friends, I'm going to stop with f-bounded polymorphism. This is its fundamental limitation. Once we bring our class hierarchy down one level, then f-bounded polymorphism stops being effective. So can you think of a solution? I'm going to give a thought exercise for you to think about. If you would like to simply continue, then feel free. Otherwise, feel free to pause the video and think about how you would strictly enforce the breed method to return the correct type. think of a very different way. So give up f-bounded polymorphism and bounded types altogether. So, do you have a solution? I have a couple of approaches, and the fundamental technique that I'm going to use here, instead of bounded types and self-types, I'm going to use type classes. This will be a solution number 4. Even though we have now found out about f-bounded polymorphism and now know what it does, let's explore this question a little bit further. So if you remember, type classes means that I extract some functionality in a trait typed with some type parameter, and then I use implicit classes or implicit conversions from our little cat, dog to those type classes. So in our example, I'm creating a trait called animal. And before that, let me comment out all the code that we wrote before so that we don't have name conflicts. Okay. And let's extract our little breeding method to a type class. Let's call this type class canBreed. This receives a type parameter, and this will have a small method, let's say breed, which receives a value of type A. This will be our cat or our dog, and this will return a list of A. So we are basically forcing from the type class that a cat will breed to a list of cats and dogs must breed to a list of dogs. So we enforce the method signature directly from the type parameters here. Now, if we declare, for example, the class dog, which extends animal, then in its companion object, I can create some implicit conversion to a canBreed instance. So we can say object dog, and we can say implicit, say object dogs can breed, which extends this canBreed dog. And in the breed method, we would need to take a dog instance, and this will return a list of dogs. Okay, and the implementation is not really important. We are only concerned with the type correctness. So a dog must breed to a list of dogs. So if you remember now from the type class pattern, we already have 2 of the 3 steps already completed. We have the type class description and the type class instance. Now we are left with a 3rd step, which means converting dog to some implicit class, which has a method which can receive an argument of this guy as an implicit parameter. So let's define an implicit class. Let's call this canBreed ops or enrichment of type A. And this receives an animal of type A. And let's say this has a method called breed, which receives an implicit argument of type canBreed. Of type canBreed A. And this will just return a list of A. And the implementation is going to be simply calling the breed method from this instance. So we say canBreed.breed with the animal that we pass here as a parameter. So if we later say val dog equals new dog, then we can safely say dog.breed, because now breed is an implicit method in the sense that dog is auto-converted to a canBreed ops. So the compiler does new canBreed ops of dog with our little dog passed in. So it has access to the method breed, which takes an implicit parameter. Now, of course, at this point, the compiler will search for potential implicit candidates, which in this case are found in the object here, which is part of the companion object of the type involved in the breed call. So the implicit value here to pass to breed is going to be dog.dogscanBreed. So the compiler will then pass it to the method breed inside. So this will be the final method call when we simply say dog.breed. But for us, this is a really nice API because we can simply say dog.breed and we are sure that this will return a list of dogs. Now, I understand that starting from the original problem, this solution might be a little hard to wrap your head around, but if you understood type classes, this shouldn't be too hard. So we implemented the type class pattern by first defining the type class's methods, then defining type class instances as implicit objects or implicit values, and then the third step, converting our little object of type dog, for example, into something which can have access to our type class instance, which has a method called breed, which receives an implicit argument, and the compiler is then free to search for an implicit candidate to pass in here, which it will find in the companion object of dog where we declared the type class instance. Now, at this point, we've only answered one part of the question in the sense that we've made sure that dog breeds to dogs. That is because we wrote correct code. Now, the second part of the question is how can the compiler force dogs to breed to dogs even if I made mistakes? So how does the compiler signal mistakes to me? Well, let's try to write some bad code saying, for example, class cat extends animal, and saying again an object cat, and let's define our type class instance wrong in a wrong way, saying implicit objects cats can breed extends can breed dog. So notice that this is perfectly compilable code, but that's until I say, for example, val cat equals new cat, and then I try to say small caps, and then I try to say cat.breed. The compiler signals the breed method that it's implicit, that is, it belongs to this canBreedOps class, but if I try to compile this code, notice what's happening. The compiler yells at me saying could not find implicit value for parameter canBreed. That is, the cat companion object does not have the right type class instance type. What this means is that the compiler tries to find an implicit candidate to pass into this method of the canBreedOps class, and it cannot find an implicit canBreedCat instance. We only have this little guy, which is of the wrong type. So the compiler is, okay, I cannot find a canBreedCat instance. So we cannot lie about our types even if we wanted to, or even if we made mistakes, the compiler is sure to catch them for us before we run the code. This is pretty cool. Now, a small criticism for this method in terms of concepts. Notice that the trait animal doesn't have any more methods, and the class dog doesn't have any more methods as well. We only have the breed method in some type class, and we define some implicit type class instances and conversion classes and so on and so forth, but the actual method in class dog is not there anymore. We've split the API between the trait animal and this abstract canBreed trait. So let's simplify things. I'm going to comment this code away, and I'm going to consider the possibility of the trait animal being the type class itself. So let's say we have the trait animal, and this is typed with a type parameter a, and this has a small breed method, read, which takes an instance of type a and returns a list of a. So the animal trait is the type class itself, so pure type classes. This is our solution number 5. By keeping the API here inside the concept that we want to represent. And in part 2 of the type class pattern, we would just say class dog is a standalone class, and we would make it adhere to the type class by saying object dog, and inside we would create a type class instance for dog, so implicit object dog animal, say, equal or extends animal dog. And inside we would override breed as a list of dog, and we would just return something. Okay, So we have our part 2 of the type class pattern already implemented, and then we need some kind of conversion class. And then let's say we have an implicit class. Let's call this animal ops, or animal enrichment, which takes a type parameter and we pass an instance of that type. So this wraps an animal. And this also has a, let's say, breed method, which gets an implicit argument. So implicit, let's say, instance or animal type class instance, to be super specific, and this is an animal A. And this returns a list A, whose implementation is going to be simply calling the breed method out of this argument. So animal type class instance dot breed with the animal that we supply here as a parameter. So animal. Okay, and then we say val dog equals a new dog, and then we are free to say, lower caps of course, we are free to say dog.breed. So as you see, much cleaner code with the same properties. Again, if I create a class called cat and an object called cat with a wrong implicit value, so if I say class cat and object cat with an implicit object called cat animal, which by mistake extends animal dog, then if I say val cat equals new cat, and I attempt to say cat.breed, the compiler will fail to find the right implicit argument, because the cat animal here, the implicit object, extends the wrong type. So the compiler is able to catch that for me before I actually run the code. Alright, so a bit of an abstract lesson, although we wrote quite a bit of code. I hope you found this video useful, and I'm waiting for you in the next one.